Hi everyone, thanks for attending this tutorial. So in this tutorial, we will discuss recent artificial intelligence techniques used in data preparation, including early successes, limitations, and research opportunities. Data preparation refers to the process of transforming raw data on the left into a format that is useful for analysis, modeling, and other data-related tasks as shown on the right. So these tasks including discovery, ETL, integration, and so on. And if we consider each individual task, such as table search or entity resolution, we call it a single task in this tutorial. In practice, it is always iterative, so we call it a data preparation pipelines. Traditionally, it involves a lot of human efforts to orchestrate this pipeline, and recently it has been revolutionized by artificial intelligence, especially AutoML techniques. So in this tutorial, we will focus on AI techniques for both single task and also data preparation pipelines. And for artificial intelligence, we will first mainly focus on foundation models, and the term foundation models was coined by Stanford researchers. And in this tutorial, we don't differentiate between foundation models and language models because both are mainly based on transformers. So first, we'll briefly go over the decoder-based architecture for the transformer models, and we'll discuss 3 common ways of using foundation models. The first one is called fine-tuning. So basically, what you do is you load some foundation models like a bird. You use a small number of training data to fine-tune your model using 20 to 30 minutes, for example, and you can achieve the sorted results. The second way of using foundation models is embeddings or representations. Basically, you only use encoder that encode the input object like image, text, or tables into vectors, and you can use vectors for semantic search or for classification. Third way is called in-context learning. So basically, you can simply ask questions called zero shot, or you can provide a few examples called few shot. So in context learning, the difference is that you don't change the parameters of the models. Okay, so this is the outline of the tutorial. In part 1, we'll talk about how to do the in-context learning for single tasks. That means we don't change the parameters of the models. Part 2, we'll talk about how to fine-tune these language models or foundation models for single tasks, for example, for entity resolution. And part 3, we'll talk about AI-assisted data preparation pipelines. For this kind of work, language models are not widely used yet. So we'll talk about meta-learning, genetic programming, and reinforcement learning. So let's go to talk about part 1, foundation models, in-context learning for data preparation single task. So we'll mention about early successes. So especially the question about whether foundation models can wrangle your data. So this is a vision paper from Stanford researchers. So we'll show that, for entity matching, how to do the correct prompt to foundation model like GPT-3 and get answer of match or not. And similarly for data cleaning error detection, you can give an input tuple, you can prompt it, ask the foundation model to say, hey, whether this error or not. And also because of the powerful language model like ChatGPT, you can ask them to generate the code. So we also show the code generation by examples. So for example, if we provide examples from Nantown to Downtown, we can say, can you generate Python code to do this kind of string transformation? And the ChatGPT can generate pretty decent code with explanations. Although this, we have seen these early successes, but also we have witnessed a lot of limitations. So we'll talk about limitations from the prompt sensitive. If you use different prompts, if you use examples different orders, you might get a very different result. And also it's data sensitive that, take entity resolution, for example. So for some data set, the foundation models can say everything match for data set 1, but for data set 2, it can say everything don't match. So we'll show examples about this data set sensitive. And the third one is not reliable. And also we'll talk about it's not up to date, not complete. It's very poor reasoning, especially for tabular data, and it's not explainable. And afterwards, we'll talk about 3 research opportunities. The first one is called table learning. And actually, this is a workshop from machine learning community. So basically, what they have seen that they have put a lot of efforts of learning computer visions, text, and even self-driving cars. But the problem of table learning has long been overlooked. But table learning is so important, so they want to say, hey, people from machine learning community should work on this about how to better learn tables with specialized modules. And from our community in VLDB 2021, we have 2 papers talking about how to use transformer-based models to learn tables. And if you're interested, they also tutorial last year in VLDB 2022 give pretty comprehensive summary of table learning using transformers. It's the first opportunity. The second one is called routing-based method with modular architecture. So instead of using one huge language model like ChatGPT to answer all the questions, so the AI21 lab proposed a system called Miracle to solve the problem. So the basic idea is that they have many experts. Expert could be, let's say, it could be weather API, could be a database, could be a calculator. So instead of using the language model to solve all the problems, so the language model can route the question to corresponding expert to solve the problem. Okay. The third opportunity is the retrieval-based models. So large language model like GPT or ChatGPT, they encode everything into their parameters. They answer the question by using their parameters to generate output. But the retrieval-based idea try to separate the language models and the database information. So in retrieval-based method, for any question, it will retrieve or search relevant data set, tuples, or text from the database and put this into the model to be answered. We'll talk about the retrieval-based data cleaning work along this line. So we also give the conclusion about the positioning of, so whether foundation models can help and their limitations, and we'll also talk about promise interaction. Thanks.
Hello everyone, in this tutorial, we will introduce the related works in pre-trained language models for data preparation. In the field of the natural language processing community, although various deep neural networks like recurrent neural networks RNN and convolutional neural network CNN have been widely applied to improve the performance. However, since the neural network always have plenty of parameters and the datasets of most tasks are not large enough, the trained models are likely to overfit and fail to generalize well. To overcome these problems, PLMs are designed to learn unified or universal representations on large corpus so as to benefit the downstream tasks. Now we will introduce the basic concept of PLMs, which can generally classified into 2 categories. The first generation PLMs is not contextual embeddings. This kind of embeddings learn good embeddings without much considering the downstream tasks, which are hard to capture high-level property in context. The second generation PLMs is contextual embeddings. Unlike the first generation, the embedding of a word changes dynamically based on the context and can distinguish different semantics. The difference between them is whether the embedding for a word dynamically changes according to the context it appears in. There are some examples belong to the non-contextual embeddings. For example, the SIGMOD model, an efficient method for learning high-quality vector representation of words from large amount of text data. The training objective is to find word representations that are useful for predicting the surrounding words in a sentence or a document. We now introduce how to leverage the pre-trained word embeddings, that is the non-contextual embeddings, to achieve a good performance on data preparation tasks. First, I will introduce entity resolution. As a core problem of data integration, entity resolution is to determine whether 2 data instances refer to the same real-world entity. Although the pre-trained embeddings can improve the performance, large amounts of training examples are necessary, and the data scientist has to design complicated neural networks. Hence, recent study about the second generation's pre-trained models mainly leverage transformer-based models to generate highly contextualized embeddings based on fine-tuning over downstream tasks. For example, for entity matching, one of the contextual embedding methods is D2. Furthermore, recent studies have focused on how to leverage PRMS to build a unified architecture to support common data matching tasks like entity matching, entity linking, entity alignments. Finally, we will introduce some open programs of pre-trained language models for data preparation. The first program is about automatic domain knowledge injection. We have two research questions. The first is about can we automatically identify and collect domain knowledge in the wild? And the second is about can we encode various types of domain knowledge by designing a model-agnostic interface. The second problem we want to ask is about data imputation. Can the contextual embeddings generated by pre-trained language models benefit the data imputation task? And the third open program is about domain adaptive data augmentation. Can we synthesize label data by considering the domain adaptation problems?
In this part of our tutorial, I will introduce the AI techniques for orchestrating data preparation pipelines. I'm Zhu Fan from Yimei University of China. This is the outline of our tutorial. I will first introduce the motivation of orchestrating data preparation pipelines. Then, I will describe the research challenges. Next, I will present three types of data pipeline orchestration methods, namely manual pipeline orchestration, automatically pipeline generation, and human-in-the-loop pipeline generation. At last, I will describe the open problems of orchestrating data preparation pipelines. First, I will present the motivation. Real-world data preparation usually requires a series of steps, such as data wrangling, data cleaning, and feature engineering. Thus, data preparation pipelines are used to formulate the workflow of multiple steps where data moves from one step to its subsequent steps. This is one example. To generate prepared data, a data scientist first joins multiple tables. Then, she fills missing values and finally reduces dimensionalities via PCA. Traditionally, the pipeline is always orchestrated by expert, which is time-consuming and hard to discover the optimal solution. So we have two challenges. The first challenge is large and complex search space. Even a simple pipeline is composed of several steps, where each step can be implemented by different algorithms. Moreover, there may be complex dependencies among different operators or algorithms implementing the steps. For example, the choices of missing value imputation may help some feature engineering operators while harming others. Therefore, it is very challenging to explore such a large search space. Secondly, the performance of a pipeline, or even each operator, heavily depends on downstreaming tasks and the distribution of underlying data size. Therefore, there is no pipeline dominating others, and given a new task, data scientists have to evaluate different pipelines. The entire process is very time and effort consuming. Okay, then I will introduce manual pipeline orchestration, which is orchestrated by expert. This is one example of a manual pipeline. It is usually orchestrated by expert and presented as user handwritten script. There are 6 steps in this pipeline, namely dealing outliers, feature augmentation, removing irrelevant features, encoding, scaling, and train test splitting. We can find that manual pipelines usually contain many user-defined functions. and user can easily leverage their domain knowledge. To analyze manual pipelines, we classify the data preparation operations as data cleaning, encoder, scaler, feature transformation, and feature selections. And we crawl 800 notebook from Kaggle and analyze the usage rate of some data preparation operations. We can find that users are only willing to use a few operations, such as standard scaler and getDummies, whose usage is close to 30%. Most operators are rarely used, whose usage is less than 10%. We can also see that few users use data preparation operations. There are more than half pipelines that have no data preparation operations, and most of the remaining ones only use one data preparation operation. So we can get the pros and the cons of manual pipeline orchestrations. We can see that manual pipelines are very flexible and can be easily injected with domain knowledge and user experiences. However, the disadvantage of manual pipeline orchestration is that the pipelines may have blind spots. That means data scientists may not be aware of complex but useful operators, such as polynomial features provided by sklearn. Therefore, the data scientists rarely try different combinations of operators to find the best one. This observation inspires us to introduce more automatic pipeline generation methods and human-in-the-loop pipeline generation methods. Due to the time limit, I will briefly introduce the representative techniques. More details can be found in our conference tutorial. First, I will introduce automatic pipeline generation. This is a high-level overview of the techniques we will present in our tutorial. In general, we will introduce three types of automatic pipeline generation methods. The first one is inspired by AutoML. The basic idea is to use Bayesian optimization and the meta-learning method to find the best pipelines. Representative methods include AutoWeka, AutoSKlearn, TensorOBOE, and UplandMiddle. The second type uses genetic programming to optimize the entire pipeline. And the third type uses reinforcement learning to find the optimal data preparation pipelines. The representative methods include learn-to-clean, DeepLearn, Athena, and HAPAP. I will introduce the details of each method in the conference tutorial. I will skip the details here. We will also introduce human-in-the-loop pipeline generations. This is the categories or the catalog of this type of methods. I will introduce a recommendation-based approach, including Doreen, AutoSuggest, and AutoPipeline. And I will introduce the combination-based approach such as HiPipe. At last, I will introduce program synthesis approach, including Copilot and ChatGPT. I will skip the details here, which can be found in our conference tutorials. Okay, finally, I will present open problems of orchestrating data preparation pipelines. The first one is search-based refinement. That means we need to study how to utilize human guidance to construct the search space of possible pipelines and define operations that are specific to particular tasks. The second open problem is domain knowledge injection. We need to study how to inject domain knowledge to automatically pipeline generation algorithms. The third one is smooth integration with AutoML. We need to study how to smoothly integrate pipeline generation with other AutoML tasks, such as hyperparameter tuning and module selection. Okay, this is a high-level overview of this part of our tutorial. Thank you.